Howdy guys, welcome back. Just 1 second to flick on the document camera and we'll start talking. So I am working on you guys' exams. They will be done today, but they are not quite done yet. I aimed to get them done last night, but I got another Calc 1 section that's quite large. I had a test on the same day and I just didn't quite get there all the way. But I promise I will get them done today, so don't stress. Your test grades will be out today. Today is the 17th. Just a few little announcement things. I can't say exactly what time they will be done, but I will get them done today for sure. Oh yeah, this document camera froze. I'm going to reboot the doc cam. Give me 1 second. Why it does it sometimes, but it does. Last time, I think we left off talking about implicit differentiation, logarithmic differentiation, getting ready to talk related rates. So today I'm going to pick back up there. We can look at maybe one more little logarithmic differentiation problem. There we go. So exam 1 grades will be out today. The homework is out. Let's do like it normally is next Monday. I push that out on Monday right after class. I don't think there's any other announcements. So yeah, let's just get into it. Today, we're going to talk about logarithmic differentiation. I always forget whether it's logarithmic or logarithmic. I always say logarithmic in my head. Differentiation. And related rates. So, and then of course, on Friday, we will have our next student lecture. That will be fun. Let me take a look here, see what order I put these things in your homework. I can grind through them in that order. Let's show you guys. Okay. So yeah, we talk about inverse trig functions, implicit differentiation, a bunch of related things there. And then we get into derivatives of log functions. Yeah, and then some related rates. So sadly, there's some logarithmic differentiation stuff that's not in your homework that I wanted to talk about. I don't know why, but these problems aren't available in WebAssign for me to add to your homework set. But last time, so let's do it. More differentiation. Last time we saw that if you have like a big product or a big fraction and you want to differentiate it, it can be really nice to expand using the log rules before you differentiate. I think we saw an example problem. Oh, where'd it go? Went away. We saw an example problem somewhat similar to. Oh, these, where'd it go? Somewhat similar to like this, right? We wanted to differentiate some big nasty thing like that. And the way we did it was by taking the derivative after taking the log. Yeah, something like this, right? And we take the log, then expand, then differentiate. Let me go ahead and work number 20 here just as a fun example. So recall, it's sometimes wise to take ln and expand before differentiating. And an example could be, yeah, something like this. So what was the function? We have y equals sine to the 6 tan to the 4 over x squared plus 3 quantity squared. So I want to find y prime where y equals some nasty thing like this, sine to the 6 tan to the 4 over x squared plus 3 quantity squared. You could, of course, jump right in with the quotient rule, right? That is doable. But the derivative of the top would require a combination of power, product, and chain rules. The derivative of the bottom is a power and chain rule thing. And then you'd have to, of course, use the quotient rule to glue all that shit together. So low d high minus high d low all over low low. That's going to be a lot of differentiating. So instead, we can take the natural log on both sides, and I get the natural log of y equals the natural log of sine to the 6 tan to the 4 over x squared plus 3 quantity squared. And I can expand that as natural log of sine to the 6 plus natural log of tan to the 4 minus natural log of x squared plus 3 quantity squared. And then we can bring the powers down. This is 6 ln sine of x plus 4 ln tangent x minus 2 ln x squared plus 3. So the natural log of y, rather than y itself, the natural log of y can be written like this. And each one of these little pieces is very easy to differentiate using the chain rule. So apply or differentiate on both sides. We get, on the left, the derivative of the natural log of y is 1 over y times y prime. That's the chain rule, right? Derivative of the natural log function is 1 over the inside, and then you have to multiply by the derivative of the inside. And that's the rule everywhere here. So kind of, I should say the kind of thing that's running in the background here is that the derivative of the natural log of x is 1 over x. This is the thing that we're using in the background. So if I want to take the derivative of 6 times the natural log of sine x, I'll get 6 times 1 over the sine of x times the derivative of sine x, which is cos x. This piece differentiates to this. This guy, I'll have 4 times 1 over the tangent of x times the derivative of tangent is secant squared of x. And then minus 2 times 1 over x squared plus 3 times the derivative of x squared plus 3, which is 2x. And we can clean this all up quite a bit. This is the same as saying y prime over y equals 6 cos x over sine x plus 4 secant squared x over tangent x minus 4x over x squared plus 3. And I think you would agree that every step here is pretty simple, and certainly simpler than diving right in with the combination of quotient, product, and chain rules that you would need here. The last thing we have to do is to multiply it back over by y, because I want y prime. So since I want y prime, I'll multiply both sides of this expression by y. And that'll give me y prime equals all of this. Cosine over sine, that's cotangent, so I might as well write this as 6 cotangent of x. Secant squared over tangent, that probably does cancel somewhat nicely. It's 1 over cosine divided by sine over cosine. Actually, it doesn't. No, it doesn't cancel very nicely. So I'll just leave that as 4 secant squared x over tangent x, and this piece is just 4x over x squared plus 3. All of this times y, right? Y prime over y equals this, so y prime equals all of that times y. Just multiplying both sides by y. And then the very last thing we would do is substitute in what is y. Well, y was sine to the 6, tan to the 4 over x squared plus 3 squared. So y prime, let me write it like this. So y prime is all this stuff, 6 cotangent x plus 4 secant squared x over tangent x plus 4x over x squared plus 3 times y. Well, y is the 6th power of sine x times the 4th power of tan x, all divided by x squared plus 3 quantity squared. And this is your derivative. This is the same thing you would get if you used the quotient, product, and chain rules on the original thing. It looks a little bit different. It's in a different form than you would get if you just jumped in straight away with the quotient, product, and chain rules. And in a lot of ways, this is nicer. But that's it. This is y prime. And you'll notice it's an explicit expression. It's not an implicit expression. Oh, did I lose a sign? Yeah, I might have. Yes, that should have been negative. Thank you, thank you. This is a minus. Good eye, thank you. Okay. So are there any questions on what we did here, where this is coming from? Okay. Something that I'm not talking about with my non-honors class, but I do want to talk about with you guys, are some functions that can only be differentiated logarithmically. So I'm going to tab away for a second and look at something cool here. Like I said, this isn't in your homework, because for whatever reason, I can't find these problems in the new version on WebAssign. Used to have them in there, don't see them now. But have you ever considered a function like this? Ignore the stuff on the left. This. X to the x. It's a weird function, right? It's not a power function because the power and the base are both variable. It's not an exponential, and it's not a power function. It's not either of those things. If the power was constant, then this would be a power function. If the base was constant, then this would be an exponential function. But both the power and the base are variables. And so this presents a real challenge. So there's one last thing before we leave the section on log derivatives. Let's find f primed of x for the function f of x equals x to the x. The issue here is that we can't use the power rule. X to the x isn't a power function because the power isn't constant. And I can't use the exponential rules like b to the x primed equals b to the x times the natural log of b. Remember, this was the rule we used for general exponentials, because x to the x isn't exponential because the base isn't constant. So kind of the only sort of rules I have that look like they might apply to something like this are either the power rule, where you bring down the power and subtract the power by 1, or the exponential rule, where like some number to the x can be differentiated as b to the x times the natural log of b. Neither of these apply. The power rule requires the power to be a constant, and the exponential rule requires the base to be a constant, and I'm not in either of those situations. So what we do instead is use logarithmic differentiation. Instead. So if you're trying to differentiate a function where both the base and the exponent are variable quantities, then you need to use logarithmic differentiation. So if I take the natural log on both sides, I get the natural log of f of x is equal to the natural log of x to the x. And the natural log of x to the x is the same as x times the natural log of x. Right, this power here can come down like this. So we have already here again, the natural log of f of x is equal to x times the natural log of x. So now if I differentiate on both sides, I can apply the operator d dx to both sides. The right-hand side, this is going to require a little product rule. The left-hand side, I know how to differentiate the natural log. This is going to be 1 over f of x times f primed of x by the chain rule. And on the right-hand side, I do my product rule. The derivative of x is 1, so this is just ln x plus x times the derivative of ln x is 1 over x. So I arrive at the expression f primed of x over f of x equals natural log of x plus 1. And from here, I can multiply both sides by f of x to get f primed of x equals, I'll have ln of x plus 1 times f of x. Like this. And then my final move here is going to be to substitute in for f of x. F of x is x to the x. So I get f primed of x equals the natural log of x plus 1 times x to the x. And that is f prime. So we have to use logarithmic differentiation here. It's the only way to do it. The other place you run into this is if you take that function that defines the number e, like 1 plus 1 over x all to the x, he requires this as well. So let me assign to you guys an extra little bit of homework. This isn't something that's going to be collected, but you should really do it. I would like you guys to find the derivative using the same sort of methods. This is extra homework for honors. Find f primed of x for the function f of x equals 1 plus 1 over x all raised to the power of x. And my hint is to use logarithmic differentiation, beginning with the natural log of f of x equals the natural log of 1 plus 1 over x to the x. And your first step will be an algebra step. You'll need to bring this x down in front of that. All right, I'll leave it there. You guys can grind the rest of that out. It's not hard. It's just like the last example. But you know that as x goes to infinity, this gives you the number e. So there's something quite special about this function, and its rate of change is therefore automatically interesting. So I want to really encourage you guys to look at the derivative of f and maybe even ask yourselves, what does that derivative do as x gets larger and larger and larger? All right, if you want to see this worked out, ask me at the start of class, not Friday, because that's going to be a student lecture, but at the end there when we have a little discussion. Okay. We need to talk about related rates. So that's what we're going to jump to now. Let's do it. And then on Friday, Julio and Chris are going to talk about differentials. So let's get this related rate stuff sorted out. This is a little bit challenging. It's a lot of fun though. You just have to have the sort of right perspective to see it. So I'll say, imagine that x is equal to a function of time and y is equal to a function of time. But x and y are not necessarily functions of each other. So it's kind of like implicit differentiation, only instead of assuming that y is some function of x, I'm going to assume that y is a function of time and x is a function of time. So they're both free to move around on their own. Then if I take the time derivative d dt of x, I would get dx dt. And if I were to take the time derivative d dt of y, I would get dy dt. The normal derivative d dx of x would be 1. But here I'm not differentiating d dx, I'm differentiating d dt. So the variable down here tells you what you're considering the variable to be for the sake of the derivative. And since x is a function of time, I get dx dt out. Also, if I have something more complicated, like d dt of x squared, this would require the chain rule. I would get 2x times dx dt, or if I had something like d dt of the sine of y. Again, I'm differentiating with respect to the variable t here, not with respect to the variable y. So you have to take the derivative with respect to y and then multiply by the derivative with respect to t. So here you would get cos y times dy dt. It really is the same chain rule stuff. It's just the chain rule, but it's being used implicitly, and it's being used with respect to a new variable, not x or y, but with respect to the variable t. So just give me a feel for how comfy you are with these sort of expressions, especially the last two. Are there any questions about where the pieces in the last two expressions here come from? Oh, sweet. Then related rates is a collection of problems. I messed something up. Yeah. So sine of y, I want to take the time derivative d dt of sine of y. So I differentiate the outer function, sine becomes cosine, and I leave the inside alone, y stays y. So this is differentiating the outer, leaving the inside alone. And then by the chain rule, I have to multiply by the derivative of the inside. So I'm just kind of showing you examples of how the differentiation mechanic works in this setting where x and y are both functions of some third variable, time. So am I answering the question, or am I missing the point of the question there, Tahan? Don't be shy. I'm just making it. I'm just making this shit up. Yeah, these are just examples. Yeah, these aren't. Neither of these are coming from anywhere special. Totally just made them up as examples. Yeah. Sorry. Yeah, I see how that would be confusing. Like, is this related to that? No, totally different things. Just pulled it out of my ass. I'm sorry. Okay. So let me show you one of these like kind of simple related rates problems, and then we'll increase in complexity. Suppose I tell you that the area of a square is increasing at 4 centimeters squared per second. Can you tell me how fast is the side length changing? Is the side length growing at the moment when the side length is, well, let's say 1 centimeter. So the idea is I've got this square, right? And I know that it's growing. It's growing at 4 square centimeters per second. So its area is increasing this fast. Every second, the area adds 4 centimeters squared, 4 square cm. How fast is the side length growing? Well, that depends on the moment you look, right? If the square is real small and the area is growing like that, then the side length might be growing at some speed. If the square is bigger, but the area is still increasing at that constant rate, then the side length might be growing faster later. So how fast is the side length growing at the moment when the side length is 1 centimeter? The first step for these is pretty much always to draw a picture. Draw a picture, figure out what's changing, and give those things variables. Since I'm talking about a square, I know all the side lengths are the same. I'll call the side lengths x. And I'll call the area A. All right, and these are all squared. Then we know the area of a square is just the square of the side length, right? It's x times x. So your first step is always to draw a picture and label things. Anything that changes, we label. Since the square is growing, right? I know this son bitch is getting bigger. That means x has to be changing, the side length has to be changing, and of course the area is changing. Those are the only two things that are involved here, and they're both changing. So we give them each a variable, and then we find a relationship between the variables using geometry. Then we ask, what do we want, and what do we know? We know that the area is increasing at 4 centimeters squared per second. That means dA dt, the rate of change for the area with respect to time, like how fast is the area changing over time, that's why this notation is so nice, dA dt is equal to 4. And we want to know how fast the side length is changing. Well, the side lengths are x, so I want dx dt at the moment when x, the side length, is equal to 1. I'm leaving off the units here because the units are all in centimeters. But if the units were in different things like centimeters and feet or centimeters and meters, you would either want to write the units like cm squared, cm, or you'd want to do a conversion, put everything into SI units, something like that. I've got my relationship between the quantities, and I've got the things I know here and the things I want here. How can I make this or this show up here? So I want dx dt. I know that a is equal to x squared. Is there a way that I can take this and make this show up?
You take the derivative from both sides.
Yeah, exactly. We take the derivative on both sides, specifically the derivative with respect to time. So we know, since a is equal to x squared, that the derivative of a has to be equal to the derivative of x squared. And then the derivative of a, taken with respect to time, that's dA dt. And on the right-hand side, the derivative of x squared taken with respect to time is 2x times dx dt. And I would pay careful attention to what happened over here. I want to make sure you're really comfy with that. It's a chain rule thing. I differentiate the outer, leaving the inner alone, and then I multiply by the derivative of the inner. The trick is that I'm differentiating with respect to time, not with respect to x, not with respect to a, with respect to t. So the d dt derivative of x squared is 2x times dx dt. Here's the derivative with respect to x, and then here's the derivative with respect to t, and we multiply them. That's the chain rule. Now I take the stuff I know, and I try to get the stuff I want. So now we know that dA dt is equal to 4, and we want dx dt when x is equal to 1. So plugging these in, we get dA dt, that's 4, equals, I want dx dt when x is 1, so that's 2 times 1 times dx dt. So I just take everything here, I plug in the stuff I know to try and get the stuff I want. So this is the same as saying 4 is equal to 2 times dx dt. And that means that 2 has to be equal to dx dt. Just divide both sides by 2. So the side length is growing at 2 centimeters per second. And that's it. This is our sort of simplest possible related rates problem. So we want to make sure we understand this all the way before we start doing more complicated ones. So take a second, make sure your notes are clear and correct, and then let me know what questions you have. So the chain rule is useful here because we're assuming that both, so think about this, right? In this physical situation, the area changes over time, right? The square is growing. So A is a function of time. And also, since the area is growing, the side length has to be growing. So X is a function of time. So secretly, A is like f of t, and X is like g of t. So let's think back here for just a second. Secretly, A is like some little function of time, and X is like some other little function of time. I don't know what those functions are, but I know that they both change over time. So d dt of A is really d dt of f of t, which would be f primed of t, which is dA dt. And more importantly, d dt of x squared is like d dt of g of t squared. And this is a chain rule thing, right? This would be 2g of t times g primed of t, which is 2x times dx dt. So it's sneaky stuff. It definitely is sneaky stuff. But kind of in the background, we're assuming this, right? This is the implicit assumption. That's why we say that we're still using implicit differentiation. We're differentiating this expression implicitly with respect to the variable t. And so each of those derivatives works out how it does because we're using implicit differentiation on the chain. Unfortunately, it looks like my black pen is on its last leg. It has given up the ghost. So I'm gonna have to switch to this orange color. I hope you guys don't mind. If you have a hard time seeing something, let me know. I'll get more pennies soon, I promise. Any other questions on this one? Don't be shy if you have them. This is the perfect place to ask these questions because the problems are going to get a little more complicated from here. There's a bunch of ways to read this expression. And I think it's worthwhile. If you look in the textbook, they have some problems at the very start here, like if v is the volume of a cube with side length x, express dv dt in terms of dx dt. That's really what we've done here. We express dA dt in terms of dx dt. And one way to say this is like, how fast is the area growing? It depends on two things. It depends on how fast the side length is growing, but it also depends on how big the side length is at that moment. Right? So a bigger square, if the edges are growing at a constant speed, then a bigger square's area will get bigger faster than a smaller square's area. If you have a little bitty square growing at some constant speed, so the edges are expanding at some constant speed, then the area isn't growing as fast as if you have a big square with the edges growing at some constant speed. So a fun thing to do with these sort of relations, these are called differential equations, by the way, and this is the language that the universe is written. All of physics is differential equations. This right here is a differential equation, and it tells you how the area's rate of change compares to the side length's rate of change. And it's very much worth your time, especially if you're at all interested in any sort of engineering or physics, to think really hard about what this differential equation is saying. It says that the rate of change for the area is proportional to the rate of change of the side length. But the thing that you're multiplying by here isn't actually a constant, it's the side length itself. So the speed that the area changes depends on both the side length and the speed that the side length itself is changing. I'll let you think about that. I encourage you to think about that. But while you do that, we're going to look at, or well, having tucked that in our pocket to think about later, we will move on to the next problem. Again, I'm going to have to change color here. Let's say we've got a balloon. Say air is being pumped into a spherical balloon at the rate of, let's say, 3 cubic inches per second. So I've got air being pumped into a balloon. The balloon is always in the shape of a sphere. I know that's not 100% realistic, but at 3 cubic inches per second. I would like to know how fast is the radius growing at the moment when the radius is 6 inches. So our first step is to draw a little diagram. Here's my balloon. It's in the shape of a sphere, and it has a radius. Distance from the center of the balloon to the edge is the radius of the sphere. I know that the volume of any sphere is V equals 4/3 pi times the radius cubed. So definitely the things that we're interested in here are volume and the radius. Those are the only things that the sphere has to tell us. Air is being pumped into the balloon, so the volume is changing, right? Because we're adding air, that means the balloon's getting bigger, so the volume is going up. And as the volume goes up and the balloon gets bigger, that means the radius must be going up also. I want to know, how fast is the radius growing at the moment when the radius is 6 inches? So as this balloon blows up, it gets bigger and bigger and bigger and bigger. If you kind of freeze time at the moment when the radius is 6 inches, how fast is the volume growing at that moment? I can attack this by differentiating, but first I want to ask, what do I know? And what do I want? Air is being pumped in at 3 cubic inches per second, which means that dV dt, the volume of the balloon, has to be increasing. So dV dt is positive at 3 inches per second. So I'll just write 3. And what do I want? I want dr dt at the moment when r is equal to 6 inches. So first you draw your picture, then you write down the equation relating the variables of interest, then you write down what you know and what you want. And then you ask yourself, how do I make this shape and this shape show up? And the clear answer here is to differentiate. We differentiate this equation implicitly with respect to the variable t. So I apply d dt to both sides. Four thirds and pi are both constants. So I get on the left dv dt, and on the right 4/3 pi just pops out. And the derivative of r cubed is 3r squared. But then because I'm differentiating with respect to time, I need to multiply by the derivative of the inner function with respect to time, which is just dr dt. Sorry, I gotta get my cat off the table. Nala, kitty, get down. Get down, kitty. Good girl. So here is my differential equation relating the rate of change of the volume to the rate of change of the radius. I want dr dt at the moment when r is 6. I know that dv dt is 3. So now I just plug all this stuff in. We can cancel the 3's here. They go away. So really, I'll write down one last form of this before I plug stuff in. dv dt is 4 pi r squared times dr dt. Now, plugging 3, 4, dv dt, and 6 for r, we get 3 equals 4 pi times 6 squared times dr dt. And that means dr dt has to be 3 divided by all this stuff. That's 3 divided by 4 pi times 36. So pi times 4 times 36. 36 has 2 factors of 3 that I can cancel in here. 36 divided by 3 is 12. 12 times 4 is 48. So this is 1 over 48 pi. So that's dr dt. That's how fast the radius is changing. We can approximate this to get a better feel for it in the calculator. One divided by 48 pi. Well, that's about 0.0066. And this is inches per second. So at that moment, the radius is growing quite slowly. And we've seen this, right? You guys have experienced this. As you're blowing up a balloon, watch next time how fast the balloon expands as you add air. If you're blowing as fast as you can, you're adding air at pretty much the same consistent volume. In other words, dV/dt is pretty close to a constant, like 3. At first, the balloon seems to expand slowly, but then the balloon feels like it expands very quickly towards the end, right? This is a fascinating thing to experience as you do it yourself. So I encourage you to play with this and try to enjoy it and try to see it in the context of these sort of problems. Any questions on this one? Okay. There are a few more problems like this that I would like to work with you guys. There are some fun ones that are purely mathematical. There's one other one that is like real worldy and I think is fun and worth looking at. 2 questions from the same problem choice. Yeah, this is good. Let me do one more real world one and then we'll do something something a little bit different. So I'm going to look at number 17 here. One goes south, the other goes west. So 2 cars set off from the same point. One goes south at a generally constant speed, we'll say 60 miles an hour. And the other guy goes west at 25 miles an hour. I don't know, how fast is the distance between them changing 2 hours later? Right? That's a real world example. Again, we should draw a picture, assign variables, and then write down an equation. Once we've written down the equation, we should identify what we know and identify what we want. Then we'll take a derivative, plug in the stuff we know, and solve for the stuff we want. So here's the starting point. One car is going south at 60 miles an hour. So call this car 1. And I know he's going south at 60 miles per hour. The other one goes west at 25 miles an hour. I guess I should do it like this. It's going west, 25 miles per hour. And the idea is, let me redraw this here. This is kind of silly. Start here, instead of drawing those, here's car 1. And I know he's going south. Here's car 2. Let me think of them as points. It'll make life easier. Hey, this guy's going 60 miles per hour. And this guy's going, what do you say, 25 miles per hour. The reason I'm redrawing it with these as points is because I'm going to want to think of there as being a triangle in here. This is my start. I need to get in here and label some distances. So the distance car 1 has traveled south from the start. I can call that, how about y? And the distance that car 2 has traveled west, I can call that x. And then if you think about this, there is a right angled triangle going on in here. So from the picture, we get that x squared plus y squared is equal to, I don't know what to call this. Let's just call it d. Equal to d squared. D is the distance between the two cars, isn't it? D is sort of, oh, actually, I shouldn't call it D, god damn it, because we're going to use D for derivative. We're going to use T for other things. What do we want to call it? So I call it L for length. This is equal to L squared. Sorry. So let L be the length of the distance between the two cars. You could use D here, but then you're going to write things like DD, DT, which can look complicated. So the one car is going south at 60 miles an hour, the other car is going west at 25 miles an hour. And when you draw that out, you get a little right triangle here. The hypotenuse of that right triangle is the distance between the two cars. Right, the straight line distance from car 1 to car 2 is this hypotenuse. So according to Pythagoras, x squared plus y squared has to be equal to L squared, that hypotenuse squared. So now I can take derivatives on both sides. Maybe before I'll go ahead and do it here because we've already written it. This means 2x times dx dt plus 2y times dy dt is equal to 2L times dl dt. Because all of those are functions of time, right? They all change over time. X is changing over time because the car is moving to the west, car 2. Y is changing over time because car 1 is driving south. And L is changing. As both of those cars move, the distance between them is surely increasing. So all of these are functions of time. They all need to be differentiated implicitly like that. What do I want and what do I know? Well, I know that this first car is going west at 25 miles an hour. That means dx dt is 25. And I know that the second, I know this car is going this way at 25 miles, and I know that this car is going down at 60 miles an hour. So I know that dy dt is 60. I want dl dt at the moment 2 hours after start. So I can plug in the things I know. Right, here's my little bits of information, my know and my want. I can plug in the things I know, dx and dy. So I've got 2x times dx dt. Dx dt is 25. Plus 2y times dy dt. Dy dt is 60. Equals 2L times dl dt. I want dl dt. First, let's divide everything by 2. That will get me 25x plus 60y equals L times dl dt. Now, in order to solve for dl dt here, I need to know what is L, what is y, and what is x. And that's where this 2 hours is going to come in handy. So this relationship right here is always true. It's true for any moment. I want to know specifically at the moment 2 hours after the start, what is dl dt? So I need to know 2 hours after start, what is L, what is Y, and what is X? So to answer the question, we need X, Y, and L on 2 hours after start. Let's start with X. 2 hours later, X is going to be what? Well, I've been going 25 miles an hour for 2 hours. That means I've gone 50 miles. Y, I'm going 60 miles an hour for 2 hours. So Y will have been 120 miles. And L, I'll have to calculate. So, and L squared is X squared plus Y squared. So L squared is 50 squared plus 120 squared. In other words, L squared is, I'm not about to do that arithmetic in my head. Do I still have Lambda? I don't. So that's Desmos. So this is L squared equals 16,900. So here's that. And this means L has to be the square root of 16,900. Which is 130. So at the moment in question, 2 hours later, I know X is 50, Y is 120, and L is 130. So I can plug all of these in here. So 2 hours after setting off, we have 25 times 50 plus 60 times 120 is equal to 130 times dl dt. And this is an equation we can easily solve for dl dt. 25 times 50, 60 times 120. So what is 25 times 50 plus 60 times 120, all divided by 130? 25 times, I'll just do arithmetic here. So this is 8450 equals 130 times dl dt. I saved the question in chat there. What was the question there, Haley? Or did I make an error somewhere?
He calculated the answer.
Say it one more time.
I think he calculated the answer for you.
Oh, nice. Yeah, thank you. Let me just double check that. So we've got 8450 divided by 130. Yeah, shit, thanks. Yeah, so 65 is dl dt. So at that moment, 2 hours after the cars set off, the distance between them is increasing at 65 miles per hour. Neat stuff, right? So this is related rates. They tend to be some of the harder problems in Calc 1 because you have to go from something that looks like this, just a sentence, to a diagram, and you're responsible for picking the variables and labeling the diagram and coming up with the equation and differentiating and figuring out a strategy. There's a lot to do here. So I strongly recommend that you look in the textbook and read this. They have a problem-solving strategy here, which is very good. Read the problem, read it carefully. Draw a diagram. Introduce notation. What they mean by this is label things, right? So like where we labeled this as X, we labeled this as Y, label things. Specifically, make sure you label anything that changes over time. And then ask, what is it I want and what is it I know, right? I know that the car 1 is going 25 miles an hour, the car 2 is going 60 miles an hour. Okay, so in terms of my labels, that means dx dt is 25 and dy dt is 60. Also, what do I want? I want dl dt. Then we take the geometry of the situation and use it to write down an equation like this. And then you differentiate. And then you see what you need to solve for the thing you want, right? So you differentiate, then plug in the stuff you know. I knew that dx dt is 25 and dy dt is 60. So I differentiated, and then I plugged in 25 for dx dt, plugged in 60 for dy dt. Clean everything up and ask, okay, what other shit do I need to get the thing I want? The thing I want is dl dt, but there's still all these other unknowns. There's L, Y, and X in this equation. So now we come over here and solve for any of the missing pieces. Then we can plug in and get our answer. So these are challenging problems that require you to think strategically and also to work tactically. You need to be good at the tactics. The tactics here is like differentiation and algebra. You also need to be good at the strategy, which is like setting up this, what do I know, what do I want, and kind of figuring out how to get there, labeling things, drawing pictures. So practice these things. How are we doing on time? I don't think I have time to solve the remaining problem that I was interested in solving here. So let me take a quick look. One of these is a lot of fun. They say, suppose y is square root of 2x plus 1, and assume y and x are functions of t. This is a little different than I wanted. Yeah, this is fun. So a particle is moving along a hyperbola, reaches this point, the y coordinate is 2. Yeah, maybe we'll do one of these later. I don't want to dump too much on you right now. So I'll go ahead and wrap it up here because we don't have time to do a full problem. But the ones that I've put in your homework are fairly simple. You should be able to tackle them without too much trouble. And this will free us up on Friday to learn about differentials and linear approximation. I think the differentials and linear approximation stuff, I'll go ahead and put that on next week's homework. So you're free to just learn about it this Friday, take good notes, finish up the homework as it is. I think it's long enough. And next week's homework will have the 3.10 stuff, which we'll be learning about from Chris and Julio on Friday. And then on Monday of next week, Kevin is going to teach us about min and max problems. And then I'll put all of that stuff on next week's homework. The related rates will be where this homework week finishes. And then differentials and min-max problems will be on next week's homework. Any questions from me before I let you guys go for the day? Alrighty, thank you guys so much for coming. Again, I promise I'll get your exams done today. Don't panic, we're almost there. I'm about 3/4 of the way through my last class before I can get to yours. So about 10 more other people's exams to grade, then I'll get your guys done. It shouldn't take more than a few hours, so probably by 5 or 6 tonight. Have a good afternoon, and if there's anything I can do for you guys, don't hesitate to reach out. Canvas messages, emails, office hours, all good. Take care, guys.